So EM algorithm. I will first motivate the problem which will lead to the EM algorithm. And then secondly, I will apply it to some problem. In this case, let's take Gaussian mixture models, which are a lot seen in practice, or at least in school. So first, motivation. Let's assume we have some kind of joint distribution. We know, right? And then we would like to optimize, and this joint distribution is specified by some parameters we don't know, right? And then what we normally do is we do maximum likelihood, and let's do this for this case. So we have logarithm of p from x, which is log of from e to n from p from xi, and normally we can maximize this, but we don't know xi, or we only know the joint distribution or how to factorize it, right? So what we do is we have still this from n to 1 to n, but we have additionally this factor k from 1 to k, which is just the rule of total probability, and then we can have set I equals to k, and a lot of times this could be, for example, membership or something like that, and we know we can factorize this into I to n to k, for example, into this. And these all are, of course, parameterized by some parameters, which we would like to know, right? And then we can put the logarithm inside, which is what we normally do. But in this case, we have this nasty sum here, and this makes it very hard for us to optimize. So what EM proposes, and which is used a lot in practice, and also a lot of other cases like variational inference and stuff, they do all the same trick. So what they do is, let's write this again with this e to n log to k, and then here we have xi set I equals to k. And now what they do is they propose some kind of distribution over z equals to let me undo this, equal to like this, and this is now actually an expectation over this term here, which does not really matter for us, but now because of this we can apply Jensen's inequality, which gives us equal to n. Then we can take this outside, and we have the condition, but we know, since this is a probability distribution, we know that over every k we have q equals to 1, right? And then we can apply Jensen's inequality, which comes just from the convexity. So we can put it outside, and now we have q from z equal to k. Oh, I forgot the k here, right? So like this, and then we have log And now we have a lower bound. We have a lower bound on this term above, right? So the question now is, how do we decide what is the best Q? And to get a tight upper bound, so as close as possible to this here above, we have to choose P of Zi equals to K given Xi. So what we get is equals to N from K over all K's. So what we get is this P from Zi equals to K given Xi. Z equals to K, and then here Z equals to K. And again applying this substitution. And this is basically all the stuff we need for the EM algorithm. And now the E step is basically just this. So let's take blue. This is the E step, and then maximizing over everything will be the M step. So I shortly summarize. E step is calculating P Zi equals to K over Xi, and the M step is maximize. So we have arg max over all possible parameters, right? Like we normally do in in maximum likelihood, over all n, over all k. Here normally this gets like rewritten in some fashion, for example in like this, or a lot of people use this, so it does not really matter. I will use this 2 here. So let's use ik, and then log, because it just symbolizes that this is now constant. And this is important when we later optimize, because this is the thing that normally makes it nasty to optimize. Now I could again just rewrite this as this. And now let's do a quick example where we can actually apply this. So I've just rewritten here the EM algorithm from before, and now let's state the problem. So in GMM we have, or we know that for a given cluster a data point is distributed like this. So for a given cluster we have some normally distributed points, and the probability that some cluster is chosen is normally written like this, which is just a mixture which sums to 1. For example, it could be everyone, you initialize it so that everyone is equally probable, something like that. Then let's do the E step, which is pretty simple in this case. So set E equals to K given Xi. Here we just apply Bayesian rule, which is Xi equals to K equals to K, and overall P of Xi And of course this can be rewritten as sum over all k so xi given SE equals to k, so E equals to k, which again of course is just this. And those two are of course clear, so this is just normally distributed and this is just normally distributed as stated above. And then the M step is a bit more complicated, but actually not much. So we just take the argmax over all the parameters, and in this case I will just write like this, then sigma and this, but of course we have for each cluster these three parameters, right? And I have now written the sigma, but of course it's just a covariance matrix, so it's not just one, it's multidimensional, or it can be multidimensional, does not really matter. So this is then equal to ek, and I have to write here of course equal ek, right? And then logarithm, and let's directly write the right stuff here. So we have Gaussian distribution, which is something like this, and then exponential with xi minus mu over covariance matrix inverted, again mu, and of course those are all parameterized with the k. I forgot the sum, I'm sorry. Like this. And when we take argmax, we have to take the logarithm, not the logarithm, the gradient with respect to the function, and or with respect to mu, for example. Let's take for mu. So let's do like this, and then I will leave the argmax out. So this is ik, and now I will split up the logarithm. So we have log of 1 over 2 pi determinant, and then plus logarithm of an expectation. I saw here I forgot to multiply with this mixture distribution. So we have log of expectation, which is just the part of the expectation, right? Okay, and then again we have a log of this. And I forgot another thing. Of course, I forgot here the distribution, the division through ik, which I now have to add here too, and additional with a minus sign, right? So log of this. And since we optimize, or we take the derivative with respect to mu k, all the terms without the mu k will just fall out, which is this and this. I have to say, of course, mu k will some be in there somewhere, right? But since we took the expectation over this in the e step, this will, like, we can consider it as an constant, so it just falls out. Of course this term will fall out, so what we're left with is, and now I take the uk into the sum. Let's do that also. So this goes in here, and what the effect will be, we have only, so since it's for a specific k, the sum of the k's will fall out. So we're left with like this, and then uk, and we have xi minus mu k transposed like this. Okay, and this is equal to I think this is equal to -1, right? Of course, I have to do this like this, and then the xi's, and again the -1, and this time for the mu k. And since we're taking the derivatives, we want it to be 0, right? So that we get the maximum. Yeah. So we just factor it out. Okay, -1 xi, which is equal to 1 to n, again ek, and I took it to the other side instantly, of course. And I forgot this -1 to k. And now we can just kill this here, and then what we're left with is uk, mu k is equal to into 1 to n, ik x1 over to n uk. And it, of course, for a GMM it's pretty simple, or has this nice intuitive explanation that that it's like a soft clustering, where these are just the probabilities that xi belongs to the cluster k. And then it makes all very much sense, because if this is 1 or 0, in case of a hard clustering, what we get is like a mean, right? So we sum up all the xi's if e is in k, and then we divide it through e element to k just once, which is equal to number of elements in k, right? In k, which is just the mean, of course. So let's recap for a second. Here we saw that why we can't calculate it, or here we saw it why we can't calculate it because of this nasty sum inside the logarithm. We saw that we can, through this nice multiplication here, we get an expectation, then we can pull it out, apply Jensen, which gives us a lower bound, then how to choose Q. And here is the moment where some algorithms choose something different, variational inference, for example, or some ray tracers use their different techniques to generate light, for example, for another practical stuff. Then we saw that how which is the E step and which is the M step, and maybe here to write this makes it constant, right? Then here just the algorithm in full, and then here for the GMM, what's the E step and what's the M step, and then the stuff on how we get, for example, for μk. And of course, you have to do the same thing for the clusters and cluster probabilities and covariance matrices. Thanks.